Anybody have any homework questions? What? Do you have it with you? Anybody have the, I don't have the problems with me. 19? I can look it up. Okay. Number 19 on, what? Oh, vectors. So vectors, number 19. So there's a beam. And it's connected to the wall by a pin joint. And down here, there's a pin and slot. And we're given that this slot makes an angle of 20 degrees with the vertical. And the beam makes an angle of 45 degrees. Yep. And we know that the length of the beam is 4 meters. And we want to figure out, so from statics, you might remember that the force applied to an object by a pin and slot joint is perpendicular to the slot. So it could be this way or this way. You just get a different sign for R when you calculated it. But it has to be perpendicular to that slot, and it has to have a magnitude of R. And then the other thing we have to figure out is the vector that goes from the pin at the wall to here. Okay. So for part A, we need a vector that has a magnitude of R and multiplied by a unit vector that's perpendicular to that slot. Okay, so we need a vector like that where this angle is 20 degrees and this is a right angle. Okay. So the way to do that, and this way of thinking about angles comes in handy really often. So if this is your coordinate system, what we're trying to figure out is, and here's the x-axis, here's the y-axis. The vector we want is this. We want to represent that direction as a unit vector. But first we need to figure out the counterclockwise angle from the x-axis to that vector, okay? So the way I recommend doing that is first look at whatever angle it gives you, okay? And draw a vector on this coordinate system with its tail at the origin that's in the direction that's given here. So I'll continue there's the negative y-axis, negative x-axis. So first of all, if we put the tail at the origin, this 20-degree angle here tells us that a vector like this is 20 degrees from the negative y-axis. Okay? And so if we're trying to, what we're trying to come up with is the value of a theta that's counterclockwise from the positive x to this. So we'll start out with, so what's the counterclockwise angle from the positive x-axis to this vector? Well, it's 20 degrees short of 90. It's clockwise, not counterclockwise. So we'll start out with negative 70. And then from there, we know these two are perpendicular. So now, so we start out like this. We go -70, and now we're facing this way. And now we go counterclockwise 90, so add 90 to that. And you get an angle of +20. And so then that unit vector is just cosine of 20, sine of 20. And so the force vector then is just r times that unit vector. Which is 0.940, 0.342. I left out the r. Okay. And then the other vector, we want a vector that goes from the pin down to the pin and slot. So for that one, draw the coordinate system. I'm just going to think about it the same way. The vector we want is this, and has a magnitude of 4. The angle that we're given is that a vector this way makes an angle of 45 with the positive x-axis. So this is 45. And so you can think of that angle as 45 plus 180. So theta for this is positive 45 plus 180. So 225. And then the vector is 4 times cosine of 225. 4 times sine of 225. And that is 3.464 negative. I know the cosines and sines of every 10 degrees, and then if the numbers are simple enough, then I can multiply it in my head. 464 negative 3.464. Any questions about that? Daniel, does that make sense? That idea of like finding an angle by hopping from one to another, to a relationship to another one, that comes in handy surprisingly often. Any other homework questions? Okay. That was 19, yeah. Okay, so let's go back to what we were working on last time. I should have told you I did it as a power series. Like, yeah, I just did the cosine power series in my head. That's what I'm going to tell the next people who ask me. Okay, so back to stress tensors. Okay, so there is always a relationship that you have to remember. Let's say it's an equivalence. Between the stress element, or I'll call it the stress cube, that shows the external loads acting on a point, external, so the external load's acting on an infinitesimal cube surrounding a point, and the stress tensor. And the relationship looks like this. So here's the stress cube. And each one of these faces has 3 components of force per area acting. This one's called the XX stress, XY, XZ, and then this one is the stress YX, but we know from symmetry that that's equal to XY, sigma YY, sigma YZ, and then on the Z face, we have sigma ZX, sigma ZY, and sigma ZZ. Okay? And those are equivalent. Those tell the same story as the stress tensor, sigma with an undersquiggle, sigma XX, sigma XY, sigma XZ. Now we'll use the symmetry. So this is XY, then YY, YZ. And then we'll use symmetry for the next 2. So sigma XZ again, sigma YZ again, and sigma ZZ. Okay, and the units for all of these values are force per area, which are also the units for pressure. And so the SI units are pascals. Yep. The diagonal elements are called normal stresses. This thing is really annoying. Okay, these are the normal stresses. So what does it mean that those are the normal stresses? Well, it sort of makes sense if you look at the stress cube. What's special about those 3 in the diagonal? That's right. They're all normal to the face that they're acting on. So the diagonal elements are the normal stresses. And each is perpendicular to the face. off-diagonal elements are called the shear stresses. And they act in the plane of the face. On a given face, the three stress the three elements of the stress that act on that face, the three stress elements form a vector. And that vector is called the traction on the face. Okay, so it turns out that there's a relationship between the tractions and the stress tensor that's really useful in calculations sometimes. So the relationship between the stress tensor and traction vectors. Okay, so it turns out that if you right multiply the stress tensor with an outward facing unit normal for the face, the answer is the traction vector on that face. Okay, so let's see how this works. So let's say, for example, let's say your stress tensor is 5, 20, negative 2, 20, 0, 8, negative 2, 8, negative 10. Okay, that has all the symmetry that you need. It doesn't matter for this what the units are. Let's say it's megapascals. What is the traction vector on the x face? Okay, well, here's our cube, okay? And if you imagine the coordinate system origin being at the center. Then an outward facing vector is in that direction, okay? This is the X, the Y, and the Z, okay? So what would a unit vector be in that direction? These, by the way, okay, these outward facing unit normal vectors, you can visualize those as like from the movie Alien. Okay, so these vectors are like the alien coming up, and this is whatever that guy's name was, right, coming out of his stomach. That's what I'm talking about, like it points from the inside out. Okay, so what are the components of that vector if it's a unit vector? Yep. So that outward facing unit normal is 1, 0, 0. And so the traction vector is, okay, so I got 5, 20, negative 2, 20, 0, 8, negative 2, 8, negative 10. And I'm multiplying that by 1, 0, 0. Yeah, the vector is on the right. If I put it on the left, you wouldn't be able to multiply. What? Oh, well, it's just saying we want, so name all the vectors that are in this direction, okay, that are straight along the x-axis. There's 2, 0, 0, 50, 0, 0, 1,000, 0, 0. But whatever it is, if you divide it by its magnitude, this is the unit vector that you would get. So that's the unit vector in that direction. Yep. So that's the outward facing unit normal to the face. And if you do this multiplication, you get a vector 5, 20, negative 2. We're still in megapascals. And that's the vector of force per area acting on that face. Okay. Well, that's not too amazing. I mean, it just isolated the element. Well, the way it works is these are the three stress elements that are acting on the x face, right? And because of symmetry, that's equal to this column. And then, so this only gives you back, you know, the ones that are acting on the x face. But it doesn't just work for, you know, positive faces. First of all, it works for negative faces too. So what about on the negative y face? So we're going to take the same stress tensor, 5, 20, negative 2, 20, 0, 8, negative 2, 8, negative 10. And we're going to multiply that by the outward facing normal for the negative y face. So what's an outward facing, you know, the negative y face is the one that we can't see underneath. What's an outward facing unit normal for that face? 0, negative 1, 0. And so 0 multiplied by 0, negative 1, 0. And we get the vector, dang it. And yeah, so negative 20, 0, negative 8. Well, on the positive y face, we have the vector 20, 0, 8. Okay? So on the negative y face, we know from last class that on the negative y face, it has to be equal and opposite. So that gives you the traction on that face. Okay? So it works on all 6 of the faces. Okay? But it's actually, still, that isn't too earth-shattering. But the next thing is what makes this really useful. So what if you multiplied by an outward-facing normal at some odd angle? Okay, so for example, what if we used an outward-facing normal of 0.7071, 0.7071, 0. So that's in the xy plane at 45 degrees between the positive x and the positive y. Well, that actually gives us something meaningful. So if you calculate this traction, so I'm going to use the same stress tensor, 5, 20, negative 2, 20, 0, 8, and then negative 2, 8, negative 10, and multiply it by this vector, well, that is, I could have done this with easier numbers, that's for sure, but, oh no, I can do it though. Watch this. That's 3.535 plus 14. Can someone calculate that for me? 5 times, so 3.535 plus 14.14, and then this one's 14.14, and then I can't do that, no way. I'll do the y component and you guys do the other two. $15.5556. Okay, I'll call it 56. And then what's the third one? Okay. So what does that mean? Well, that means that here's our coordinate system. I'm drawing it straight on, so the z-axis is coming right out towards us. Okay. And say that we had drawn our stress cube. So like when we defined the stress, let's say instead of defining it with a stress cube that had all the faces perpendicular to the coordinate axes, for some reason we had decided to define it at an angle like this, where one of these faces had the outward facing unit normal 0.7071, 0.7071, 0. then if you think about this face, these values we got, 15.56, 14.14, 12.24 megapascals would be the tractions acting on that face. Okay, so there's two ways that this is useful, only one of them in our class. So remember, like when I defined the stress tensor, I said, okay, define this cube. But right when we defined the cube, we oriented it to have a simple relationship with the coordinate axes, because why wouldn't we, You define it as simply as you can. And through that definition, we came up with this definition of the stress tensor. But what if in our definition we had decided to, say, okay, for this coordinate system, this is our stress cube, and then did the limiting procedure. Then that material that has this stress tensor the way we do define it would have this traction acting on that inclined surface. Okay. So it's not super clear what the use of that is, but it's kind of amazing that the stress tensor does that. You can see how that might be related in some way to representing a stress in a different coordinate system, right? So this is useful in two ways. The first one is in defining boundary conditions for mechanics problems. We won't use this, but this is the kind of stuff that you do in continuum mechanics. So this is an important idea in continuum mechanics. So the basic way that works is if you have a material and the face over here has some loads on it, and you know the shape of that face, then because of the tractions that are actually acting on that face, there's actual loads that are creating actual tractions. You can use that relationship to put limits on what are possible stresses at the boundary. Okay, you really don't have to know any more than that. You probably don't even have to know that much for now. But the second thing is important to us. We are going to, so the principal stress is the stress tensor expressed in a coordinate system where there are no shear stresses. It's kind of an amazing fact that no matter what the state of stress is, there's some coordinate system where the only stresses are normal. Okay, there are none of those shear stresses. Um, and this is, this is important, practically speaking, for figuring out when stuff is going to break. And we'll talk more about that later. But this is a really important thing to be able to find. The derivation of the principal stress um, relies on finding those tractions on inclined faces. Okay, so this is the one that's going to matter for us in this class. And the last thing that you're going to need to be able to do with stresses is go back and forth. So there's this relationship between the stress cube and the stress tensor, and it's going to be helpful all the time to, when you see a stress tensor, at least imagine what that's saying about the loads on the stress cube. There's another thing, equivalence, that you have to be comfortable with, and that's the Voigt stress. And the reason it doesn't give you any new information, but it's a format that's going to make calculations possible that we need to do. So the Voigt stress, which I'm going to call sigma sub v, is just a 6x1 column matrix with the stress elements XX, YY, ZZ, and then YZ, XZ, XY. And literally the way I remember these still to this day is that these seem backwards. The first one seemed like the order you would pick. The last three all seem exactly backwards. Okay, so let's say we have a stress tensor that's equal to 2, 0, 1, 0, 5, 0, 1, 0, 8 in whatever units. What are first, what does the stress cube look like? Second, what's the Voigt stress? And third, what's the traction on a face that's oriented, let's say, okay, so we want to figure out the traction on a face oriented like this one, where this angle is 30 degrees. 201,050. 201,050,108. Okay, so for part A, we want the stress cube. Actually, let's make one of these negatives so you see. So let's make the 5 negative, and let's make the 1 negative also. Okay. Okay, so what does the stress cube look like? Well, on the x face, the XX traction is in the positive x direction. God, I gotta glue this button. So that's in the positive x direction. It's on the x face, and it has a magnitude of 2. Then there's nothing on the x face in the y direction. In the z direction, there's something, in the negative z direction, so it's going opposite, here's our coordinate system. So this 1 is going back this way because it's in the negative z direction. Any questions about that? So now the y face, we have nothing in the x direction. In the y direction, we have 5 negative. So this way. And then nothing in the z direction. And then on the z face, we have something in the negative x. The magnitude of 1. Nothing in the y direction. And then 8 in the positive z direction. So that's the stress cube. And you can see, if you remember, for the rules for the stress elements, the ones that said that this had to be in rotational equilibrium said that shear stresses had to have this relationship. If one is going like away from the edge, the other one on the adjacent face is going away from the edge. If it's going toward an edge, the one on the adjacent face, so like on the back here, would have to be going toward that same edge. Okay. What about the Voigt stress? So the Voigt stress, first we do the diagonal elements. So 2, -5, 8. And then we do YZ. Then we do XZ. And then we do XY. And now the last one, we want to find the traction on that inclined face. So what we have to do is find an outward facing unit normal for this face. And I'm assuming that we're talking about this coordinate system. Okay, so how are we going to find that? Well, this is kind of related to that vector problem that we did at the beginning. What we're given is that if you draw the coordinate system, a vector this way makes an angle of 30 degrees with the negative x. Okay. And then we want an outward facing normal. So we want, the alien for this material along that face has to be this way. It can't go the other way because that would be going from outer space into the material. We want outward. Okay. And so now that we have this direction, okay, like this one is a theta of positive 150. The vector we want is this way, perpendicular to it. So the angle for that is 150 plus 90. So 240. So the outward facing unit normal is cosine of 240, sine of 240. And this is all happening in the x, y plane, so z is 0. And so that is negative 0.5, negative 0.866, 0. Again, just do the power series. And now multiply that to the stress tensor. So the traction is 2, 0, negative 1, 0, 5, 0, 0, 0. Oh, that 5 was negative, and then this is 8. And we're going to multiply that to the vector negative 0.5, negative 0.866, 0. Oh, yeah, thanks. Can I do this? Possibly. What? Yeah. Yep, negative 0.5. And so that is negative 1 for the first element, positive 4.33 for the second one, and positive 0.5 for the third one. And so, like for example, if this was happening in an actual, engineering situation, and your stress tensor at the points on the edge, because remember, each stress tensor just represents a point. So we're talking about points on the edge here. If they all happen to be this along that whole edge, okay, we calculate that traction. That traction has to agree with what external loads are actually being applied to that face. Okay, because that face is actually, this face that we're calculating the traction for would actually be the outer edge of the material. And so you'd look at the loads, you divide by the area, you calculate the components of those forces, those force per area. And if it didn't match that traction, then you'd know this stress was wrong. Okay. Any questions about that? Okay, so over the weekend, I'll give you some problems like this, and basically it's just getting comfortable going back and forth between these three ways of representing the loading at a single point. That's all.